First question is how to draw pressure, volume and temperature entropy diagram for regeneration Rankine cycle, which is thermodynamic vapor cycle. Second question, solve one problem on regeneration Rankine cycle by using Mollier diagram and steam table. Let us understand how to draw pressure, volume and temperature entropy diagram for regeneration Rankine cycle. As this cycle is thermodynamic vapor cycle, steam is used as a working substance. If we observe the diagram, here is boiler, turbine, steam extraction, then the condenser, low pressure pump, open feed water heater and high pressure pump are the main components through which steam is passing when the different processes are taking place. Now we will consider what is the initial condition of the working substance. We will consider 1 kilogram of saturated water is entering inside this boiler at pressure P1, volume V1 and temperature T1. Now we will show this point 1 on the diagram as well as on this graph. So here at the entrance of the boiler I will show here point 1. Now what is the phase of at the initial condition? So phase of working substance is saturated water. That is, we have to show point 1 on the saturated liquid line for this pressure, volume and temperature entropy diagram. So we will select here point 1 at pressure P1 and here is volume V1 and here also saturated liquid line I will select here point 1 at temperature T1 and entropy S1. Now we will move for the different processes. So what is the process 1 to 2? So process 1 to 2 is the heat addition at constant temperature and constant pressure. So if we observe process 1 to 2 is taking inside the boiler. So I will show here the point 2. So what is the amount of this saturated water? That is 1 kilogram. So here this saturated water is getting converted into superheated steam and we have to show this process 1 to 2. Now condition is that pressure will remain constant, temperature will also remain constant. So what is the effect of heat addition on this volume and entropy? So volume is also getting increased and entropy is also getting increased. So we will show here process 1 to 2. So point 2 is for the superheated temperature. So I will show here. Now how to show 1 to 2 on this temperature entropy diagram? So point 2 is for the superheated steam. So this temperature will remain constant only up to phase change process is taking place. That means this saturated water is getting converted into saturated vapor. So I will show here straight horizontal line. Now what is happening after that? So as we continue to add the heat to the saturated vapor, because the phase will remain constant, so its a temperature is getting increased as well as entropy is also getting increased. So we have to show after that increase in temperature as well as increase in entropy. So here will be point 2 and the corresponding temperature I will show T2. So this process 1 to 2 is getting completed. Now what is the heat supplied during this process? So heat supplied, that is nothing but change in enthalpy, that is H2 minus H1. Now we will move for the next process, that is process 2 to 3. So process 2 to 3 is the intermediate steam extraction. Now superheated steam, so we will say that 1 kilogram of superheated steam enters inside the turbine where the isentropic expansion is taking place. But what is happening? During the process 2 to 3, here intermediate steam extraction process is taking place and I have shown here for steam extraction with the help of this red line. So what is the amount of steam extracted? That is equal to m1 kilogram. So I will show here point 3 and this steam is passing to the open feed water heater. So we have to show from turbine to open feed water heaters. This is the steam extraction is taking place. So here is the partial expansion. Partial isentropic expansion is taking place, and after that m1 kilogram of steam is extracted at point 3 and passing to the open feed water heater. And due to partial isentropic expansion, work is done. So this work done we will show here as a work done 1. Now we have to keep in mind what is the state of the working substance at this point 3. So at point 2 here is superheated steam, and at point 3 steam will be dry and saturated steam. So we have to show the location of point 3 on saturated vapor line. So how to show isentropic expansion? So what is happening during the expansion? Its a pressure is getting decreased, volume is getting increased, and due to decrease in pressure, temperature is also getting decreased. And we have to show entropy constant because here isentropic expansion process takes place. So we will show here process 2 to 3. On pressure volume, pressure decreases and volume increases, but we have to show point 3 on the saturated vapor line. So I will show here in this way. Here will be point 3. Now we will move for the next. Temperature is getting decreased. Now we have to keep entropy constant. So we will draw straight vertical line up to this saturated vapor line. So here is the point of intersection. Here is the point 3. So what is the work done 1? So work done 1, that is for the partial expansion, work done 1 is equal to change in enthalpy, that is H2 minus H3. Now we will move for the next, that is process 3 to 4. So here process 3 to 4 is the complete isentropic expansion. So how we can say this is complete expansion? So this expansion, that is isentropic expansion, taking place up to condenser pressure. So here is the condenser pressure. So I will show here 0.4. So here is the complete expansion is taking place. Now we have to show this process 3 to 4 on this diagram. So how to show? So during expansion, pressure is getting decreased, volume is getting increased. And here also temperature is getting decreased, but we have to keep entropy constant because this is isentropic expansion. But what is the phase of the working substance at point 4? So here it is wet steam. So remember at point 4 wet steam is there, that is because of this expansion up to this condenser pressure, steam will become wet. So we have to show here decrease in pressure, increase in volume. So I will show in this way, and I will show 0.4. So this 0.4 will be in between the saturated liquid line and saturated vapor line. Now in the same way we have to show here temperature entropy. So temperature will also decrease and entropy will remain constant. So here I will show 0.4. So 0.4 should be in between saturated liquid line and saturated vapor line, that is it is wet steam. Now what is work done 2? Because here full expansion is taking place, so work done 2, that is nothing but again change in enthalpy. But what is happening? Because during the process 2 to 3 m1 kilogram of steam is getting extracted. So what is the remaining weight of steam? So if we observe here at the point 4, there is 1 minus m1 kilogram. I will show here 1 minus m1 kilogram of steam is there. So we have to take here 1 minus m1 kilogram during the process 3 to 4. So here work done 2, that is equal to, we have to take this amount of steam, that is 1 minus m1 multiplied by change in enthalpy. So change in enthalpy, that is H3 minus H4. Now we will move for the next process. So process 4 to 5. So process 4 to 5 is taking place in the condenser, that is cooling process, or we can say heat rejection process. So I will show here 0.5. but this heat rejection process is taking place at constant pressure and constant temperature. So what is the effect of cooling on other parameters, that is for volume and entropy? So its volume is getting decreased as well as entropy will also getting decreased. Now remember, what is the state of working substance or phase of working substance at point 5? So at point 5 we have to show phase, that is saturated water. So we have to extend this point 4 up to this saturated liquid line. So we will show here. Here will be point 5 and corresponding pressure will be P4 equal to P5, and here will be volume P5 and here will be volume P4. Now in the same way for temperature entropy we have to show decrease in entropy and temperature will remain constant, and here will be 0.5. So here T4 is equal to T5 and here entropy is 5. This process we have to show arrow also. Now if we observe here, the cooling process is taking place. So because of cooling, enthalpy at point 4 is more than the enthalpy at point 5. So how to take the enthalpy difference, that is H4 minus H5. And one more thing, that is what is the amount of steam that is getting condensed. So here 1 minus m1 kilogram of steam that will move to the condenser. So we have to also consider 1 minus m1 multiplied by H3 minus H4. Now we will move for the next process, process 5 to 6, which is pump work by low pressure pump. So we will show here process 5 to 6. Now if we observe, here is the work input which is known as WP1. Now what is the effect of the work input during the process 5 to 6? So here due to work input, pressure is getting increased. So as pressure is getting increased, temperature will also getting increased and volume will getting decreased. And this pump work is the isentropic process. That means we have to show constant entropy. So we will show this process 5 to 6. So increase in pressure and decrease in volume. So I will show here the 0.6. Then in the same way we have to show entropy constant and increase in temperature. So from this 0.5 we will extend this line up to this, that is here will be our 0.6. Now how to show pump work WP1? So we know that this pump work WP1 is nothing but the change in enthalpy. So enthalpy at 0.6 minus enthalpy at 0.5 multiplied by what is the amount of steam or amount of working substance. So here working substance is 1 minus m1. So it is continue from condenser to the low pressure pump. So we have to write here 1 minus m1 multiplied by H6 minus H5. So this is the pump work. So this is the low pressure pump. After that there is high pressure pump. So we will give here the suffix 1, that is WP1. Now again we will move for the next process. So next process is the process 6 to 7. Here is the open feed water heater, and in this open feed water heater direct mixing process is taking place. So what is the direct mixing process? So here is m kilogram of steam is entering inside this open feed water heater, and here is the saturated water is entered inside this open feed water heater, and here direct mixing process is taking place. So we have to write here mixing for steam and water, that is here is the water at 0.6. So if we observe the location of 0.6, that is it is the water at this 0.6 is mixing, and the mixture will become saturated water. So remember this mixing up to this saturated water. So we have to show 0.7 on the saturated liquid line. So after mixing we will show here the 0.7. So in the range of 6 only I will show here 0.7. I will join this 6 to 7. Then in the same way I will join here, I will show here 0.7 on the saturated liquid line and I will join this 0.7. So we have to show arrow also. Now remember from this 0.3 here, from this 0.3 m1 kilogram is also reached to this open feed water heater, and this whole mixture, that is for this m1 kilogram of working substance and 1 minus m1 kilogram of working substance mixes here. So this m1 kilogram is from this 0.3. So we have to also join this 0.3 and 7. So I will join this 0.3 and 7 by this dash line. So in this way we will join this. Now we will apply steady flow energy equation. That is the enthalpy at 0.7. So we have to show from this 0.6 here will be 0.7. So what is the enthalpy at this 0.7? That is equal to enthalpy of working substance at 0.3 plus enthalpy of working substance at 0.6. So we have to show that. So I will write here enthalpy at 0.7, that is H7 is equal to. Now enthalpy at 0.3, that is equal to m1 kilogram of working substance. So we will write here m1 multiplied by H3 plus enthalpy at 0.6, that is H6, and what is the amount? That is 1 minus m1. So 1 minus m1 multiplied by H6. Now we will simplify this. So H7 is equal to m1 H3 plus H6 minus H6 m1. Now we will take m1 as a common term. So m1 H3 minus H6 plus H6, which is equal to H7. Now we can solve this for m1. So how we can write the value of m1 in term of enthalpy? So if I take m1 as it is, then I will transfer this H6, that is H7 minus H6 divided by, I will take this H3 minus H6, which is equal to m1. So we can use this formula also to calculate m1, that is in terms of enthalpy. Now we will move for the next process, that is the process 7 to 1. So at this 0.7, what is the phase of working substance? That is, it is saturated liquid. Now this process 7 to 1 is again pump work by high pressure pump. So this pump work is known as WP2. So how to show this WP2? Now this 1 minus M1 plus M1, that is equal to 1 kilogram. So what is the amount of the working substance at this 0.7? That is equal to 1 kilogram. I will write here. So for 1 kilogram, what is the pump work? So here is also pump work that is added to the working substance. So what is happening? So if we add the work, then its pressure will getting increased, then its temperature will also getting increased. So we have to show this. So here the saturated liquid, that is the phase of the working substance, will remain same from 0.7 to 0.1, because we know that for this 0.1, what is the phase of working substance? That is, it is saturated liquid. So we have to show this 0.7 to 0.1 along the saturated liquid line. And what is WP2? That is, WP2 is equal to change in enthalpy. So change in enthalpy, that is H1 minus H7. Now we will understand important formulas with the help of diagram. We will calculate net work done. So net work done is equal to turbine work minus pump work. Now in turbine, 2 times isentropic expansion is taking place. So during the process 2 to 3, we have to take the change in enthalpy. So change in enthalpy is H2 minus H3. and for the remaining amount of working substance, that is during the process 3 to 4, again we have to take the change in enthalpy. But here the amount of working substance is 1 minus m1 kilogram. So we will take here 1 minus m1 multiplied by h3 minus h4. Now we will take minus sign, and inside the bracket we will take here the pump work. So two types of pump, low pressure and high pressure pump. So for the low pressure pump, we have to take the change in enthalpy multiplied by the amount of working substance. So amount of working substance is 1 minus m1 kilogram. So here we will take this square bracket. Inside this bracket 1 minus m1 multiplied by h6 minus h5 plus we have to take the change in enthalpy for this high pressure pump. So for this high pressure pump, amount of working substance is 1 kilogram. So we will simply take H1 minus H7. So this is the formula that we have to use for the calculation of net work done. Now we will move for the efficiency of regeneration Rankine cycle. So we will use formula 1 minus heat rejected by heat absorbed. So heat is rejected during this condensation process in condenser. So what is the amount of working substance? That is 1 minus m1, and we will take the change in enthalpy, that is h4 minus h5 divided by heat absorbed. So heat is absorbed during the process 1 to 2. So we will take the change in enthalpy, that is h2 minus h1. We will solve one question. Consider a regenerative vapor power cycle with feed water heater. The steam enters the first stage turbine at 80 bar 500 degrees Celsius and expand to 7 bar, where some of the steam is extracted and diverted to feed water heater operating at 7 bar. The remaining steam expands through the second stage turbine to a condenser pressure of 0.08 bar. The saturated liquid exits the feed water heater at 7 bar. Calculate the enthalpy at different points, low pressure pump work and high pressure pump work, and mass of steam extracted from the turbine. This is Mollier diagram. On horizontal line, entropy is in kilojoule per kilogram Kelvin, and on vertical line, enthalpy H in kilojoule per kilogram is given. If we observe these inclined blue lines, these are the pressure lines where pressure is given in bar, and horizontal green lines are the temperature lines, and temperature is given in degrees Celsius. This dark red line indicates for the saturation line. Now, if we observe the question, then the steam enters the turbine at 80 bar and 500 degrees Celsius. And this steam enters at point 2. So, let us first observe where is the pressure 80 bar. So, if we observe here the pressure line, that is for 50 bar, and here is for 100 bar. So, in between them, there is one point, that is, or we can say one line for the 80 bar. So we will observe here the middle line in between this 50 bar and 100 bar, and after that we will select here the 80 bar pressure line. Then we will find out where is the temperature of 500 degrees Celsius. So here 500 degrees Celsius temperature is given. So point of intersection for pressure 80 bar and temperature 500 degrees Celsius, we will select here one point. And this point indicates that is the point of intersection, and we will say that this is the point 2. Now at this point we have to find out what is the enthalpy H, that will be enthalpy H2. So from this point we will draw here one horizontal line. So if we draw here one horizontal line, then here is the line. So what is the value for enthalpy? So here is 3000, here is 3500. So if we observe, here is first, second, third, fourth. This is the fourth line for 3,400. So we can say that H2 is equal to 3,400 kilojoule per kilogram. And we will note down this value. Now after that, isentropic expansion is there. And this isentropic expansion is up to 7 bar. So we have to find out where is 7 bar pressure line. So here is 1 bar, 2 bar, here is 4 bar, and here is 10 bar. So if we observe this second, after 4 bar, here is line for 6 bar, and here this is the second line is for 8 bar. So in between 6 bar and 8 bar, there is 7 bar pressure line. Now isentropic expansion is taking place. That means we have to keep the entropy constant, and we have to extend this line for up to 7 bar. So we will extend this line, that is the middle point. So here is this point. Now what is the value of enthalpy at this point? So again we will draw here one horizontal line and we will find out the enthalpy. So from this line, so we will take here new line, and here is the enthalpy. So if we observe, here is 2,500, this first line will be 2,600, second line 2,700, and after that it is 2,750. So this point will be point 3. So again we will take here, or we will note here, this will be point 3. So we will write here the point 3. So enthalpy at point 3, that is nothing but H3, which is equal to 2,750 kilojoule per kilogram. And we have to note down this. Now, if we observe the question, again there is isentropic expansion is taking place and it is up to 0.08 bar. So where is the value of 0.08 bar? So here is 0.05 bar and here is 0.1 bar. So in between them there is one point that we have to take for 0.08 bar. So again we will select one line and we will draw vertical line. So why vertical line? Because this expansion is also isentropic expansion. So we will draw here one vertical line from this point 3 and we will continue it up to this. So what is the value for this line? So this point will be point 4. So we will write here that point, that will be point 4. So I will mention here, this is the point 4, and we have to find out what is the enthalpy at this point. So again we will draw one horizontal line from this point, and what is the value? That is 2,150 kilojoule per kilogram. So enthalpy at point 4, that is H4, and we have to note down this value. So in this way, from this Mollier diagram we get the value of H2, H3 and H4. Now we will find out the value of H5. So how to find out? Now if we observe the temperature entropy diagram, then point 5 is on saturated liquid line. So to find out the enthalpy at 5, we have to refer the steam table. Now at point 5, what is the pressure? So pressure at point 5, that is we have to refer here the condenser pressure, and which is equal to 0.08 bar, and point 5 is on the saturated liquid line. So we have to take the value of HF. So value of HF at 0.08 bar, that is equal to H5, and which is equal to 173.88 kilojoule per kilogram. Now in the same way, if we observe the point 7, then point 7 is also on the saturated liquid line. So we have to refer the steam table. Now what is the pressure at point 7? That is at the outlet of the open feed water heater. So this pressure is mentioned in the question, that is 7 bar. So we have to find out the value of HF, that is for the saturated liquid line, and the pressure equal to 7 bar, that is equal to H7, and which is equal to 697.23 kilojoule per kilogram. Now at this point we will also find out what is the specific volume, that is VF. So VF7 is equal to 0.001080 meter cube per kilogram. Now we will calculate the enthalpy at point 1. If we observe the diagram, then enthalpy at point 1 is equal to enthalpy at point 7 plus high pressure pump work. So to calculate the enthalpy at point 1, we will first calculate the high pressure pump work. We will refer here as a WP2. So we know that how to calculate the pump work, that is the specific volume multiplied by the difference in pressure. Now this pump is in between point 1 and point 7. So we have to take the pressure difference in between point 1 and point 7, and we have to consider here the pressure in kilopascal. So the pressure given in bar, so we have to convert this bar into kilopascal by multiplying with 100. And we will take the specific volume at point 7, that is at 7 bar. So WP2 is equal to VF7 at 7 bar in bracket P1 minus P7, where pressure is in kilopascal. Now we will put the value 0.001080 multiplied by 80 minus 7 bracket complete into 100, which is equal to 7.884 kilojoule per kilogram. Now we can easily calculate H1. So H1 is equal to 697.22 plus 7.884, which is equal to 705.1 kilojoule per kilogram. Now in the same way we will calculate the enthalpy at point 6. Now if we observe the diagram, enthalpy at point 6 is equal to enthalpy at point 5 plus low pressure pump work, that is we will consider here WP1. So we have to first calculate the WP1. Now this pump is in between point 5 and point 6. So we will refer here the specific volume at point 5, that is at 0.08 bar, and we will take the pressure difference, that is P6 minus P5, and we have to consider this pressure in kilopascal. So pressure is given in bar, so we will multiply here with 100. So WP1 is equal to VF5 at 0.08 bar multiplied by P6 minus P5, which is equal to 0.001008 in the bracket 7 minus 0.08 multiplied by 100, which is equal to 0.697 kilojoule per kilogram. Now we will calculate the enthalpy at point 6, that is H6 is equal to H5 plus WP1, which is equal to 173.88 plus 0.697, which is equal to 174.6 kilojoule per kilogram. Now we will move for the last question, that is what is the mass of steam extracted from the turbine, and that is nothing but M1. So M1 we have formula H7 minus H6 divided by H3 minus H6. Now we will put all the enthalpies value, and answer is 0.195 kilogram.